All right, let's jump right into this explainer by starting with a dramatic and honestly bizarre historical mystery from way back in 1859. Imagine an invisible force sweeping across the entire globe, silently altering the fundamental ways humanity communicates. We're going to explore this fascinating intersection between deep space weather and the invisible pulse that literally keeps our modern world alive.
To really understand the stakes here, listen to this incredible piece of history. On September 2nd, 1859, a conversation took place between two telegraph operators on the American line right between Boston and Portland, Maine. During a massive solar storm, these operators literally disconnected their batteries. They unplugged their power. And for around 2 hours, they continued to send and receive messages using nothing but the ambient electrical current surging from the glowing auroral sky. It was the very first time on record that more than just a word or two was transmitted this way.
Section 1. The Great Storm of 1859.
Named after British astronomer Richard Carrington, who independently observed the solar flare that started it all, this event stands as the absolute most intense geomagnetic storm in recorded history. Our sun unleashed what's called a coronal mass ejection, or CME. Now, usually CMEs take several days to travel the 150 million kilometers to reach Earth, but this one, it was traveling at an unusually high speed. Researchers actually think a previous storm had basically cleared the way of ambient solar wind plasma, which allowed this massive release of magnetic fields to smash right into Earth's magnetosphere in just 17.6 hours.
The immediate result was visually stunning. The geomagnetically induced currents created auroras so intensely powerful that the night sky over the Rocky Mountains was bright enough for gold miners to literally wake up and start making breakfast. They were completely convinced it was morning. Over in the northeastern United States, people were effortlessly reading their newspapers outside at midnight just by the light of the aurora.
It's a fascinating, almost romantic piece of history, right? Telegraph pylons throwing sparks, operators getting little electric shocks. But the real question we need to ask ourselves is this: what would happen if a storm of this exact same magnitude struck our highly electrified, hyper-connected world today?
Which brings us to Section 2, the invisible GPS heartbeat. You see, the danger today isn't just to our power lines, it's to our absolute reliance on a completely hidden vulnerability. When most of us think of GPS, we think of the map on our phone telling us to take the next left. But GPS actually provides something way more critical. It's called PTTI, or Precision Timing and Time Interval. Because GPS signals broadcast highly accurate time from atomic clocks down to the nanosecond. GPS acts as this precise invisible metronome. It synchronizes everything, from global financial transactions to the internet itself, down to the exact microsecond.
And think about the massive leap in fragility from 1859 to now. Unlike physical telegraph lines where an operator could just unplug a battery and tap a key, today's wireless networks, like CDMA cell networks, demand incredibly precise GPS time synchronization. If a call bouncing between two towers isn't synchronized to within 10 microseconds, you get cycle slips, lost data, and dropped calls. Just think about a typical cellular site installation. Nearly all of the more than 100,000 CDMA base stations in North America use these small, completely exposed GPS antennas. They feed into GPS-disciplined oscillators to keep your calls connected. If that super low-power space signal is lost or jammed by severe space weather, those cellular towers are going to start drifting out of sync.
But wait, it's not just our phones. The massive, deeply interconnected U.S. electrical power grid relies almost entirely on GPS timing to function efficiently. Power companies use GPS-synchronized clocks to match phases across vast transmission networks to an accuracy of 1 microsecond. They use it to monitor power flows and quickly isolate faults. If the grid loses that timing heartbeat, the whole tightly coupled system becomes incredibly unstable.
Section 3. A trillion-dollar vulnerability.
So what actually happens when that metronome stops? Well, researchers from Lloyd's of London and Atmospheric and Environmental Research use data from the Carrington event to estimate the cost if a similar solar storm hit us today. And their estimates are just jaw-dropping. They project it could cost the United States alone up to $2.6 trillion. To put that into perspective, at the time of the study, that was roughly 3.6 to 15.5% of the country's entire annual GDP.
To wrap our heads around that staggering threat, let's look at a breakdown of just a routine, everyday power outage that lasts only 1 hour. While residential losses sit around $309 million, the commercial sector bleeds over $13.2 billion. That jump is massive. Now imagine that outage not just lasting an hour, but stretching on for days or even weeks across an entire continent, all because our timing infrastructure was fried.
Section 4. The San Diego Warning. The crazy thing is, we don't even have to guess what localized GPS loss looks like because we got a preview in January 2007. The U.S. Navy was conducting a scheduled communications jamming training exercise in the port of San Diego. Now, they weren't targeting GPS at all. They didn't even notify GPS agencies because they thought they were operating outside that spectrum. But they inadvertently overpowered the super low-power civilian GPS signals in the entire surrounding area. It stayed jammed for about 2 hours until the Navy finally realized their own ship couldn't initialize its GPS and shut the exercise down.
The resultant chaos was highly localized, sure, but it was absolutely devastating. Without that GPS timing signal, 150 cell sites in the local provider network completely dropped offline. On top of that, 20 sites in the paging provider network crashed, which actually completely shut down the naval hospital's mobile paging system. All of this chaos stemmed from losing that single, highly vulnerable timing signal for just a brief window.
Section 5. Building a resilient future.
Okay, knowing how fragile our infrastructure is, we absolutely have to back it up. We cannot afford a single point of failure like this. Thankfully, the solutions do exist. Our best defense lies in redundant timing systems. We have highly stable atomic and quartz clocks that can essentially hold the time if GPS drops out. There's also the IEEE 1588 network protocol for local areas. But the big, wide-area solution on the table is the deployment of enhanced LoRaN, or eLoRaN. This is a ground-based, high-powered radio signal that operates entirely independently of space. It can provide exact time synchronization even if literally every satellite in orbit is overwhelmed by a solar storm.
And honestly, the economics of survival here are a total no-brainer. The $36 million cost of backing up GPS with eLoRaN is pocket change compared to the $100 billion lost annually to routine power outages or the $10 billion hit from the big August 2003 blackout. Protecting our national timing infrastructure is quite literally one of the most cost-effective insurance policies we could possibly buy.
And we need that insurance because history shows us that enormous solar storms are not some freak anomaly. They are a recurring natural cycle. Proxy data from ice cores and tree rings reveal an event in 774 CE that was 10 times the size of Carrington. There was another in 71716 BCE that was even larger. And if you're sitting there thinking we're somehow immune today, well, in July 2012, a Carrington-class superstorm was observed erupting from the sun. Its trajectory narrowly missed Earth by a margin of just 9 days, literally 9 days.
Considering our profound and often totally invisible reliance on the heartbeat of GPS to run our modern world, I want to leave you with this final thought. The sun is on its own cycle, and history pretty much guarantees it will strike again. So, when the next great solar storm washes over our planet, will our modern infrastructure hold the line, or are we going to be plunged right back into the dark? Are we truly prepared?